Okay, null A and call A are subspaces, so we can find their dimension. Simple example, let's first of all find a basis for null A. What do? You take, whoa, way too thick. What am I thinking? Sure. A is row equivalent to, well, this is still too thick. Oh, so what does this mean for null A? Well, for null A, what are you doing? You are kind of throwing some extra zeros here. I'm thinking about that matrix and solving the corresponding system. So what do you get here? You get that x4 is 0, and so is x1. x2 and x3 are free. So the typical vector x in my null space looks like x1, x2, x3, x4, which is, I'm going to make this less thick. There we go, 0.3. x1, 0. x4, also 0. x2 and x3, leave them alone. Pull this apart. And you get a very simple expression, or very simple vectors here. So a basis for null A is these two guys that came out. So as I said before, as long as you reduce to reduced echelon form up here, then this will always be the basis for null A. The only confusing or difficult thing to see maybe is why these vectors are independent always. Well, how would you prove that these are independent? Well, you take a linear combination and you'd set it equal to 0. That would mean that this is 0. So x2 and x3 are automatically 0. Okay, so this will happen every time as long as you reduce all the way to reduced echelon form up here. Okay, where was I? Dim null A is 2. Okay, how about call A? So we saw before that a basis for call A can be found by looking at the pivot columns of the original matrix A. So the pivots appear in the first and fourth columns. So I take this guy and this guy. As my basis elements for call A. Say A basis for call A is 1. And what did I say? 0, 0, 0, 1. I think that's what I said. Yeah. So the first column of A and the fourth column of A. Okay, I want to note something here. I'm saying a basis for call A. Okay, notice that I'm not saying the basis for call A because there are, certainly in this case, there are an infinity of different bases. Okay, if I have a basis and I multiply this one by 10, still a basis. If I change this to a 9, also a basis. If this is a 19, anyways, you get the idea. You can scale your elements here. That will generate a new basis, as long as you don't scale by 0. And there are also other ways to find bases, different bases. Okay, so I have a basis for call A. There are 2 elements. So therefore, dim call A is 2. Okay, pause and copy. Now let's scroll way down here. Not too far. To our next topic. I want to talk about the kernel. Pause and copy, pause and copy, pause and copy. Okay, kernel of a transformation rather. Very similar to null space. Almost the same thing. Not quite, but in many cases the same thing. So it is the set of vectors that get sent to 0 by the transformation. For my first remark, I would say you should, as an exercise, check this. That is worth your time. Remark number 2. Okay, we see that if your transformation is going from Rn to Rm, okay, then it's necessarily a matrix transformation. So the kernel coincides, in this case, with the null space. Okay, let's do an example here. Pause and copy. Now we have a strange looking transformation. What does it do? It's a machine, if you will, that takes a polynomial and spits out a 2-dimensional vector. So how does it do that? Well, it takes your polynomial p and it plugs in the number 3 to your polynomial. So maybe we should do something. Do an example. T of 1 plus 2t plus 3t squared. What is that? Well, it is a 2-dimensional vector where this entry is the polynomial with 3 plugged in. So 1 plus 2 times 3 plus 3 times 3 squared. And below the exact same thing for both entries, which is 34, 27, 34, 34. Okay, that is what my transformation does. Let's see why this is actually linear. Linear. So what do I need to do? What do I need to do? What do I need to show? Need to show. Maybe not A1. Need to show that T of P plus Q is always equal to T of P plus T of Q. Okay, for all P, Q in my domain. And also that if you have t of a multiple of a polynomial, that the scalar there can come out. Okay, so let's demonstrate that. What am I going to do? T of p plus q. I'm going to start calculating here using the definition. I get the polynomial p plus q with 3 plugged in. I get that upstairs and downstairs. Okay, that's a bit strange. What does it mean to plug 3 into a sum of polynomials? Well, what it means is you plug it into the individual polynomials separately. It's a little bit weird. So we're talking about taking a number, plugging it into a polynomial or a sum of polynomials, and you have to think about that to see why this equal sign is true. Okay, now I can do the separation I want to do. Okay, why am I happy? Because I want to end up here. Okay, my eye is on the prize. The prize is to end up here. Okay. Sometimes when you're stuck in a math problem or a math proof, you just need to focus on what you want, your hopes, your dreams, and then that will sometimes reveal the path. Okay, where was I? So this is exactly T of P, and this is T of Q. So happy, happy, joy, joy. 2. T of CP is going to be is going to be vector, the polynomial CP with 3 plugged in, top and bottom. Okay, what does that mean? Okay, well, it's just going to mean C times P with 3 plugged in. Okay, you can do some examples to convince yourself on this. It's a little bit abstract, I admit. Okay, the C can come out now. And I get C times T of P. All right. That's what I want to do. Now I want to find a kernel, the dimension of the kernel, right? So I'll say, let P be in the kernel of this transformation. So what does that mean? That means that T of P is the 0 vector. What does that mean? That means by using the definition given above of T, I get this equation, and that happens if and only if P of 3 is 0. So let's say P is equal to A plus BT plus CT squared. So what does this equation mean? It means that A plus 3b plus 9c is 0. Oops. Which is to say, now should I structure this? Well, I'll just solve. So a is equal to minus 3b minus 9c. I chose to solve for a because it is the most, it was the most available letter here. When you have just one equation, it doesn't matter really which one to solve for. So what does p equal? Remember, p is this guy. So minus 3b minus 9c is a plus bt plus ct squared. So what do you get? P is equal to, by collecting like terms, b times minus 3 plus t plus c times minus 9 plus t squared. Okay, what have I done here? So pause and copy if you haven't done so already. So I've shown you that if something is in the kernel, something that looks like this, then it must be of this form. So what does that allow me to conclude? That the kernel of T is exactly the span of T minus 3 and T squared minus 9. Now, is this a basis? Is this set without the span, is that a basis? Yes, it is. I just need to check that it's independent. Is independent since its elements. I have two elements, right? And they are not multiples of each other. They're not multiple. They're not scalar multiples of each other. You may say, "Oh, wait, sir. If I go this guy times t plus 3, I get this one. That doesn't count." Okay, they are not scalar multiples. They're not. I can't take this guy times a real number and get this guy, and vice versa. So its elements are not scalar multiples of each other. Shutter. So therefore, B is a basis for kernel of T. Oh, this is a long question. Why is it a basis? Because it's independent and it spans the kernel. Therefore, the dimension of the kernel of T is 2, because there are 1, 2 elements in B.